quick summary of yesterday, of last lecture. So yesterday we did the first chapter of Intro to Thermophysics Concepts. And basically there's three main things this is the summarized over here is just the three main things you need to know from yesterday. The definitions of internal energy, of temperature, and of heat. I won't write them down because you have them already on your notes. I'll just quickly say it. Internal energy is it's an average energy. Oh, sorry. Yes, I do have to clarify this because someone on Piazza asked a great question and I should make a note. Someone asked about non-contact forces inside the system. So what I was about to say is internal energy is all the kinetic energy inside the system when the system is at rest. Remember the three diagrams I draw, that even when the object is at rest, there's energy, and those are internal energy. And then I think I wrote something along the lines of just kinetic energy, but technically it's potential energy and kinetic energy. Potential energy is not necessarily gravitational potential energy, but as I showed last time, there's electrostatic potential energy, right? Electric potential energy. There could be magnetic potential energy. So these are everything that pulls the atoms together, pulls the molecules together, what you might know as called intermolecular force. So every force in physics associates with an energy. Okay? So there's intermolecular energy. If basically it depends whether you're expressing it in newtons or if you express it in joules. Okay, one is there's pros and cons for both ways. Newtons is a little bit more visual, so you might feel that it's less abstract. Energy seems more abstract. However, force is a vector, and I know how much you guys love vectors, right? Whereas energy is a scalar. So which one's easier to do calculations with? So there's pros and cons with this. The pro of energy being easier algebraically to manipulate in your solutions because it's a scalar comes with a cost that the idea itself, it's abstracted a little bit away from it. Whereas force is very concrete, it's a push or a pull. Right? But the algebra sometimes would become horrendous when you have to resolve vectors at different angles and stuff like that. So intermolecular forces here. What are intermolecular forces? They're actually just electric forces that leaks outside of an atom. So if you have a proton, you have an electron going around it. All right, so there's an electric force pulling them here. However, you see, the proton has a very isotropic, symmetric, isotropic means in all directions, influence, right? So when the electron is on one side, there's some residue influence leaking out on the other side. These are called dipole moments. If you happen to have another atom, like just happen to have the electron on the other side, right? So now there's some positive force leaking out on this side as well that's not balanced on this side. They're perfectly neutralized, canceled out, but on the other side, they now repel each other, right? Or on the other hand, if there's an electron here, now there's a residue electric force that draws these together. So these, in total, you add up all these effects, these are called intermolecular forces. So again, being a physicist, we like to joke that all of chemistry is basically physics. If you know electric force, technically, if you understand exactly how to calculate electric force, you can calculate from first principles how all the formulas that you need in intermolecular forces. Anyway, because there's only the idea is because in the whole universe, as far as we know, there's only 4 fundamental forces, and everything you know is made out of these 4 fundamental forces. All right, so yes, there's potential energy as well that can be counted in sites. And someone in Piazza, if you haven't read that post, go and just on the search bar look for it. It had a great answer. It's basically so how do we know if energy is internal or external? It depends on the source. So if the source is like, it's just all these intermolecular forces inside the atom, right? That's happening inside the system, then those are counted as internal forces, internal energy. When you have the Earth over here exerting a gravitational pull on the box, even though it's not falling down, let's say you put it on a table, but that pull gives it a external gravitational potential energy. So that GPE is counted as external, right? It doesn't, if you're at any height, basically that's the energy from height, just purely from some distance away from another big, massive object. Right? It doesn't feel like you have energy because you're not moving, right? But imagine let's say you're standing at the top of a skyscraper in Manhattan or something like that. You feel completely stable, whatever. But as soon as you step out one step out of the ledge, you'll be immediately convinced that you have a lot of energy stored in potential that is rapidly going to be transformed into kinetic energy, right? So you do have a lot of energy, it's just potential. It's not manifested in motion yet. So quick reminder from 3A, energy cannot be created or destroyed. However, it can be transformed from one type to another type. Temperature is a measure of how much internal energy, average internal energy each molecule or each particle has. Heat is the transfer of internal energy due to temperature differences. We also introduced a few other jargons. So these three in blue is what you need to know for this chapter for exams. This is the takeaway for the course. However, I've also introduced several jargons like particle, right? I explained what do we physicists mean as particle? What do we mean by system? What do we mean by a quantity? And one more, yes. What do we mean by a fundamental law or just law in general? What do we mean by laws in physics, right? We had a brief discussion of these. So these you will not be explicitly tested on. I won't have a question to tell you to define what is a quantity in physics. What do physicists mean by quantity? We won't do that. However, these terms are something that, because it's not examined on, a lot of professors forget to define and forget to explain. We actually mean these words in a very technical sense. We do have a special meaning for these words, and they forgot to tell the students. And then that is the source of so many confusion in the next few chapters about thermophysics. And I've received hundreds of emails about this. So I want to address this right from the start. So we are all on the same page of the words I'm using, so that when we communicate, this is the importance of definition, is for communication. When I say something, I want to make sure everyone is thinking about the same thing. And it's not like when I think of particle, I'm thinking of anything that cannot be broken down into smaller pieces in the question of interest, within the context, in the situation or the problem solved of that context of interest. It doesn't break apart. That to me is a particle. But for someone who is not used to studying physics, when you hear particle, you either might be thinking of something different than I am, or just being confused and don't know. Are you talking about molecule, atom, compounds, or elements? The answer is all of the above, right? Yeah. Okay, so know what those words mean. And the idea is, okay, so now we want to find out what happens when we add heat, right? So you add some amount of heat difference onto an object, right? Onto, let's say, an object, and what will happen? And we say there are usually three things that can happen. The temperature can increase, the volume can increase, or the pressure can increase. So usually for solids and liquids, this is usually the main thing. Their pressure does not increase too much. We'll get to that in a second. But for gas, turns out it's the other way around. Actually, I shouldn't say that. For gas, all of them are equally important. Okay, so they can all increase at the same time. It depends. Okay, for example, if the gas is contained in a very soft container, like a balloon or something, and if the air warms up in the room temperature, or for some way or another you warm up the air inside the balloon can expand in volume. However, you don't put the air in the balloon, but this time you put it in a solid cylinder, a container that with solid walls. Then when you increase the temperature, the volume cannot increase. Something else have to increase, right? So a lot of you, I think, a lot of you know the ideal gas law already, right? So those are the relationships we'll get to. And I also gave you advice on how to learn new physics concepts. Instead, actually, it's not just physics, right? Remember the questions we asked: what is it? What does it do? And why do we care? In fact, I think learning any subject in college, even if you go to biology or anything, these are appropriate. And then I talked about more subcategory of divisions, right? Learn the definitions of things. First, the technical one, because we are scientists, science students after all. So we need to know the technical definitions of things. But then don't forget, try to learn the layman definition of things, i.e. try to think of a way to say it in simple English that you can explain it to a 5-year-old. This is always the litmus test I like to run through. It's often quoted to Einstein saying that if you cannot explain something to a 5-year-old or 8-year-old, whatever his quote was, then you don't understand it enough yourself. So if you understand something, you should be able to put it in simple words to explain it to someone who haven't studied the topic. Right? The technical definition, now physics specific, is you can learn I would encourage learning both the equation definition and the word definition. In the exam, you can give either. Either one is equally formal, equally rigorous for a technical definition. But after you learn it, you want to ask yourself how to measure, you want to know the quantity that is associated with that concept. So we're talking about heat and hotness and coldness in this topic. The quantity that you can measure is temperature. That's the hard quantifiable thing that you can go out and actually measure, right? And then know the symbol for it, right? So know the symbol for it. So temperature is T. We talked about that last time. And the symbol of it and the units, the SI units, ideally, right? And then a bunch of, this is the last part, which a lot of students just jump right to the end and skip the first parts and cause confusions, is formulas relating it to old concepts, right? So after you learn buoyancy, that's the example I gave, right? And then I immediately relate that to rho v, G, like that, right? So rho, you learn density, V, you know what volume is G. Now we're relating the new concept with old concepts and a bunch of other things. For example, apparent weight can be the normal force. It's basically the real weight subtract the buoyancy in certain situations. So you know what the real weight is and you know what a normal force is, and you can relate these things together via formulas, right? So that's the last step, right? So going back to here's quantity and how to measure it. It's basically what we were at the end trying to ask: how do we measure heat? In fact, how do we measure temperature? Being a little bit more quantitative, right? Being a little bit more scientific. How do we measure it? And I've talked about you use a thermometer, which means you have some liquid in the middle, right? And then you make it in contact with some, again, this is at the end of last lecture, so I'm not gonna explain in too much detail. Just a quick recap is you utilize the fundamental laws of thermodynamics. Fundamental laws, quickly, is something that we cannot derive from further basic principles. So those are the very, very basic principles. Usually, and this is the elegance of physics, is amazingly, you just have a handful of them, usually around 3 or 4. In the case of Newton's mechanics, in the case of how objects move, the basic things of how objects move, there's only 3 fundamental laws of Newton's laws, and you can know everything about how objects move. For thermodynamics, there's 4 because there's a 0 one as well. Right, utilizing the 0th law and the second law. Second law, there's actually different versions of it. We'll go through that in actually the final lecture, in lecture 9 of this part, this segment. But the first version of the second law says that heat will flow from hot to cold. Turns out, we all know this, but turns out there's no way to prove it. It has to be stated as a fact. If you feel that that's very unsatisfactory, the satisfying part is treat that as a fact, and everything else about heat you can derive from first principle. And there's no more assumptions, right? So there's only these 4 assumptions that you need to start with. So this is one. And it is so basic a fact that there it is. It's just there. So now, I think I might have not explained how you utilize the 0th law and the second law together too well yesterday. So let me explain a little bit better. Is if you have this object that you want to know the temperature of, and now let's say in your lab you have a bunch of other objects that ranges in temperature scale from 0 degrees, 10 degrees. So you have sort of a scale in your lab of objects. We're not going to, let's assume you know these temperatures, right? Now the question is, you have a new object and you want to find out what temperature, which one of it is. So what you need to do is you take the thermometer, you make it in contact over here. Okay, so now it will go into thermal equilibrium. It will register a new, it will register certain heights, right? As the volume expands, it registers a certain height in the fluid. So first of all, why does that happen? It's precisely because of second law, that heat goes from hot to cold. Okay. So if the object is hotter than the thermometer, the heat will go there, and then it will increase the volume of the fluid, and it registers a number. If the thermometer happens to be hotter, for example, if you're measuring the temperature of ice, right, then the heat will flow from the thermometer into the object that way, and then the volume will decrease because heat is going out. So when you add or subtract heat, clearly it will affect volume, right? It will change the volume, and that is what we were saying over here, right? It will do one of these things, and this is the question we want to address: how today. Okay, but let me finish the argument here first. So now, now you bring the thermometer here, and then now you can test it, right? You can, let's say you take 10 thermometers, you make them in thermal equilibrium. Oh, that's another jargon you need to know from yesterday. I had to find out already. So you make a lot of thermometers in thermal equilibrium, and then you bring them each over here, and then one of them will not move, right? For example, you bring it over here, and then suddenly, let's say you're measuring ice, right? You bring the thermometer over here, and then the thermometer stays there. So if it starts off with this height, it just stops at that height. Whereas when you make it in contact with everything else, the height will start from here, and then maybe, sorry, if that will be increase or decrease, it'll change. One of them will not change. And then now you know that the thermometer is in thermal equilibrium with this, and since this guy, the new guy, is also in thermal equilibrium with the thermometer by zeroth law, then you know that the new guy has 0 degrees Celsius. It's a very long chain of reasoning to explain something very, very stupid, very simple. However, you see how rigorous physics can get, and there's no room for ambiguity, and there's no room for questions. No, if you understand the logic and you present this, you say, if someone asks you, question you, how do you know two things are in the, or how do you measure things, and how do you know this thing? If I say, I measure this as 20 degrees Celsius, that's around room temperature, and then someone question you and they interrogate you and ask, how do you know that is 20 degrees Celsius and not 21 or 22? You present this argument and say, okay, stay with me. First, you need to accept two laws. Two fundamental assumptions, right? I cannot explain those. If you question me those, I give up. But if you accept those, I can explain anything else you throw at me. For example, this stupid question you wanted to ask, how, if you're interrogating me, how do you measure something? So this is the learning side of things. For exam side, just to also throw in a tip of the exam side, I won't question you to reproduce this chain of logic. But of course, for learning wise, I want to demonstrate this is what physics is about, right? Yeah, so take that away as a conceptual idea. Now, we can go in two paths right now. We can first, it's natural to start with looking at when you add heat to something, how will it affect temperature and volume? Since we're talking about thermometers, let's start with volume and see volume will increase. So we know that. The question is how? How do it increase? And a more important question is how much? So if I add a certain amount of heat, so the temperature increase by 1 degree, how much would the volume expand? And that leads us to our chapter 5, the idea of coefficients of thermal expansion. There's a new quantity called coefficients of thermal expansions. The symbol is alpha, and there's a couple of them. So I'll put a plural, alpha apostrophe S. Because there's a couple versions of it. These alphas will measure how much things expand, okay? So this is basically the theory, this chapter is about the theory of how much, right? The quantitative part, not just quantitative part, how much do things expand? And the reference chapter here is in Giancoli 17.4. Okay. So this is the key quantity, right? Is this alpha. It's called I'm not going to rewrite that over here. It's just what's in the title of the chapter. But what is the definition? So the definition is it's the fractional change in size per unit change in temperature at a constant pressure. All right, let me write that down first. Okay, so let's break this down bit by bit. This looks very daunting, right? So this is what these alphas is. First part is fractional change in size. The second part is per unit change in temperature. The third part is at a constant pressure. Let me address the last one first, at constant pressure. So remember, all P, V, and T can change when you add heat to something. But that is a very complicated thing to study when so many things change. So physicists, we are being very clever. We go like, let's assume things are simple. Let's look at things one thing at a time. This is the think like a physicist part of the course. You take a complicated problem and you go like, let's assume something else is constant first and analyze two things at a time. So let's assume pressure is constant. Let's focus on just temperature and size, which is about volume, right? So we'll see if temperature change, how does volume change? We'll just look at these two. Later on, we'll put, again, we're not ignoring pressure. We're just doing it in the next step. We'll look at the easiest things first. Once we're comfortable and we're happy with this, and then we're living our happy lives, and then we have spare energy, we'll go and look at the next step. So that's the constant pressure part. So now you see why we start with this. The next part is size and fractional change in size. What do we mean by, first of all, what do we mean by size? That could mean volume, area, or length. It could mean either of these. And in fact, each one corresponds to a coefficient, a special coefficient. So 3 types or 3 versions, whatever you want to call it. Let's say 3 versions. There is the alpha L, which is called the linear coefficient, alpha linear coefficient of expansion, of thermal expansion, or just, if you're being lazy, just linear coefficient of expansion. And then there's alpha A, which is the area coefficient of expansion. And then there's alpha V, the volume coefficient of expansion. So there's 3 of them. Depending if you want to see how much the length change or the area change or the volume change, then you use each of these coefficients. Being so eager at exams, as I'm sure a lot of you are, you'll probably immediately have the question, when should I use which? Don't worry, I'll address that as we look at each one individually. So let's understand this. Let me translate this black part in black ink, this definition, this technical definition in layman terms, so we get a little bit easier to understand, right? So how would I explain this to someone who doesn't do physics? It's very simple. For example, the linear coefficient of expansion, instead of saying, oh, it's the fractional change in length per unit, change in temperature at constant pressure, they will look at you and say goodbye. So you will tell them something different. You will say, it's how much the length change when temperature change. That's it. If they want to know a little bit more, tell them keeping the pressure constant. Right? That's the fine print of it. But all right, so you would say something like how much the length would change per change in temperature. So let's say if I change 1 degree Celsius, right? If I increase it from 21 degrees to 22 degrees, 20 degrees to 21 degrees, how much would the length change? Okay. And if they want to know a little bit more technical fine print, you need to say, I'm doing that at a constant pressure. Okay? So very simple. That's the idea, right? So the layman idea, it's very simple. And then you can fill in the gaps, right? That's how much the area change, how much the volume change per degree change in temperature. So just for the learning purpose, I'll use these pink color to fill in these side study tip kind of thing. So you have the technical one, you have the layman one, right? And then you now know the symbol. Right. So this, you know, the quantity, right? This is the quantity. The quantity is the coefficient, right? The symbol, because physicists are basically lazy animals, and we don't want to write English. We go into physics because we try to avoid writing English. So instead of writing linear coefficient expansion, coefficient of thermal expansion every time, we just write the symbol, and that will tell you that. Now the question is, if the symbol, that means it's a quantity. That means you can measure it. So you need to ask, how do we measure it? This I have yet to explain. And also, if you measure something, you need to know what units you're measuring things in. And this is what I get to write now. Okay. Actually, I take that back. There's one more thing in the technical definition that is confusing: fractional change. Right, so let's address that first. If you're good at math, you'll probably remember the definition of what a fractional change means. But just for fairness for everyone, let me explain that for you as well. It's very simple. It's new minus old over old. That's new subtract old, everything divide by old, okay? Or you can, this is identical to saying, remember the symbols, right? This is definition, this means defined as, this means equivalent to, or identical to, sorry, or same thing technically. Change over the original, old, right? Old or original. Depends on which word you want to use. That's the idea of fractional change. So let me give you an example. Let's say you take your test today and you get their grades back. So you have your test 1 grades. It's not out of 50, but I'm making a random example. Let's say you got 50. You got 50 points from your first test. And then the next test in the following week, you study harder and then you improve. You got 55. I don't know what is this out of. It doesn't matter. So don't get too disappointed. It might be out of 55, this test. So what is the fractional change in your grades? So the fractional change in grades, there's no one symbol for fractional change in grades, unfortunately. This sort of is, the symbol is you do this, you do change in grade over grade. That's the closest to a single symbol if you don't want to write fractional change of grade like that. That's basically using this idea, so change of something over the original. So technically I just write original grade or a subscript O or subscript 0 or whatever, but sometimes people would be lazy and just do that. So how do you calculate, let me put that in brackets. So how do you calculate your fractional change in grade? So new minus old, subtract by, which one, 50 or 55? 50, the original, because you're looking at a change. So you look at what's the fraction of the change, fractional change. So that's 5 over 50, right? That's 1 over 10, that's 10%. So what happened to you is you had a 10% increase in your grades, right? So that's so we say you have a 10% increase. So if you watch the news or the stock market or whatever, accounting or finance or whatever, when they say when they say a percentage increase, it's the same idea of it's a percentage increase. It depends whether you're expressing thing in a fraction or a percentage, right? So that's how you calculate, just to make sure everyone's on the same page. Now let's look at heat. So applying to here. So let's say you are going to heat things up and the length starts to expand from 2 meters to 3 meters, right? So we'll call this L0, and we'll call this L1, right? 3 meters, sorry. So can you calculate the fractional change? So the fractional change in length, so fractional delta L, let me be lazy, it will be what? L1 minus L0 over L0, okay? So you can plug in the number and check. That will be a 50% increase in length. So if you heat something up and then it increased from 2 meters to 3 meters, that means it's a 50% increase, right? Let's do one more. Like, what if it goes from 2 meters to 1 meter, however? Now you calculate this delta L over L, right? So technically, you see, I should write delta L over L0 if you take this seriously, right? So if you look at this is delta L over L0, but sometimes people are lazy when they just write delta L over L. If you ever see this combination of delta L over L, the L usually means L0, okay, at the bottom, the original. Whatever, you might use different symbol, right? You can use Li for initial, you can use L O for old, or you can use any type of subscript, as long as when in the exam or when you're communicating with someone, you define what you mean, that is completely fine, right? So if you calculate this, let's actually try to do it. So let's do new minus old. New is 1 meters, old is 2 meters, and original is what? 1 or 2? 2. So what's the result? 1/2 minus 1/2, and that is minus 50%. What does that mean? That's a minus 50% change. That means is, this symbol means imply, right? Implies, it means it's a 50% decrease, right? So when you translate, this is the math part, this is the English part. We're humans, we're not machines. We don't only produce mathematical answers. That is what a computer and a calculator do. We interpret data. We look at numbers and we try to give meaning to them, right? So if you see negative 50%, don't get afraid. I know people are usually very afraid of minus signs. You see minus sign, this is what it means. It just means it's a 50% decrease. Go back to the original example situation, what's happening. So, okay, so now we're ready to give the formal, the equation definition of it, right, of the coefficient of expansion. So alpha, so which one shall we start with? Normally, so note, normally things will actually expand in all directions unless you forbid it to. So things, if you heat something up, normally it will expand in every direction isotropically. Isotropically means in all directions equally. Now, sometimes you actually, let's say you put a balloon and then you in a tube, in a cylinder tube, and then now you heat it up. The only way you can expand is sideways. Now it's a linear expansion. Okay, so which one you choose? You look at this problem, and then you use your best educated guess on, is it expanding? Are you squeezing it so that it only can expand out in 2 dimensions? In that case, the area will expand, or it's fully unconstrained. So normally, if it's completely free, things expand in all directions. Okay. Then you use the volume one. Or if somehow constrained, then you use one of those other ones. All right. So let's start with the volume one, since it's the more fundamental one. So this is sometimes it is considered more fundamental. And what was it? Remember this definition was? It's the fractional change in volume per unit temperature change. So fractional change in volume, let me make it clear, right? That's the fractional change per change in temperature. So for every 1 degree change here, how much would the fraction change? Okay, so that's that. Now this of course looks very ugly. Oh, there's one more thing. Yeah, take care of this ugliness first, because there's a 3-level fraction, and we don't like 3-level fractions. So let's reduce it to a 2-level fraction. So it's often written like this. Okay, just redistribute your fractions, right? So this is, let me put a box around this. This is what you can quote as the, and do a lot of your calculations with, right? There's one more subtlety is this has to be performed at constant pressure. So if we need to emphasize that, I'll introduce a math symbol. As you, mathematicians are very brilliant at being lazy, right? So they invent a straight line and say, this is the symbol for, so whenever you straight line, it means at or evaluated at. Okay. So it's calculating the fractional change in volume per unit temperature change at or evaluated at. Technically, I should write constant P, but try to read this out loud in English, right? The fractional change in volume per unit temperature at 1 atm. That means it's constant ATM already, constant pressure already, right? So mathematicians are great at thinking of the minimum amount of word you need to write down on a paper. All right, so yeah, so that's what that symbol means. If you ever see that, sometimes some books use a, it's sort of 50-50 in the community. Sometimes people use a bracket and then a subscript like this, okay, to mean at. Okay, both is being used. Okay, yeah. All right, so similarly, how about the area and the length one, right? So you can do the same thing. So this is for the length, the linear one, and this is for the area. Okay, so these are the 3 definitions. So out of these, the most common ones to use is actually either the volume or the linear one. Okay, the area is more commonly used. The area is least used, is also used, but if I want to tell you two of them is more important, these 2 are more important. In fact, so much so that some books, including Giancarlo, has given use of different symbols. Actually, engineers I think also use this. Physicists like to take care of all the cases, right? So the Giancarlo just calls that alpha, and call the volume one beta. Okay. So if you're reading the book, he uses that. Okay, all right. So now that we know what it is, the next question is how do we use it, right? And the final question is why do we care? So how do we use it? So how to, or actually how do we even measure this at the first place? How do we measure these alphas? Well, for example, if let's start with, let's say the length one, we want to measure the length of a certain material. So it depends on the material. In fact, you can go to the textbook and look at table 17.1, and you have a list of all the alphas of the common materials that will show up in your problem. So this is another table you refer to a lot when you do your problems, right? So you have to look at, oh, for metal, is that for aluminum? Is that for lead? Is that how much it expands, basically? Remember the layman definition, just to emphasize, is how much things expand when the temperature change. Okay? It also makes sense over here. When temperature change, how much does the size increase? And the size, I mean, depends on which type of size you're talking about. So if you have, let's say, a rod like this, originally length that, right? So now you can put it under a Bunsen burner, a candle, heat it up, and then now it becomes longer like this. So what you do is you take a ruler, you measure the original, measure this, and then you just put everything together. And then you just take the, not volume, sorry, the original length, right? And then take the delta L, which is new minus old, right? And initially, you want to measure this. We talked about how to measure temperature. And so initially, let's say it's at T0, and then it's at T1. So what do you put here? T1 minus T0, right? So that will give you, right, that number. And then people do these experiments in labs. So these are what experimental physicists, in the 18th century will do, right? To just have the lab take in a dozen materials, do this experiment, and tabulate a table, and then people keep refining it. So, and then it can be used, these values can be used in engineering if you build bridges and stuff like that. All right, so how do we use it? Why is it useful? Okay. So the best way to do it is to use this practically is actually to rearrange your equation. Look at the definition over here. Look at the delta L and the delta T, is to rearrange it so that you put the delta L on the other side. Sorry, put the delta T and the L naught on the other side. Okay. You see I sometimes use capital L, sometimes use lowercase l. Again, you should know by now, it doesn't matter what symbol I use unless, as long as I clearly define what I mean by it, right? So hopefully you see where this comes from. You just take the denominator, put it on the other side. Now, this is more intuitive to read, actually, because what this reads is, so you read this as that the change in length is proportional to the original length and the delta T, the product of that. Remember, proportional to is the math concept of equals to some constant times it, right? So in this case, the constant is exactly what we call the coefficient of linear expansion, or coefficient of sum of the general expansion. So this means proportional to. So recall what does proportional to mean is if I increase something on the left, not only do the right also increase, the right side also increase, but also even more technically, if you increase this by a factor of a certain number, a factor of n, this increased by the same factor of n. Okay, so that's what proportionality means. Okay, so the qualitative part is A increase, B increase. The quantitative part is A increased by a certain amount, B increased by the same factor of amount. Now, let's understand, does this make sense? If I increase temperature, the length, the higher, if I change instead from 1 degree to 2 degrees, I change from 1 degree to 3 degrees. So from 1 to 2, that's, so what will happen? So this will proportionally change more, so that makes sense. But this is a little bit less intuitive, but also very sensible, is it depends on the original length. So if originally it's longer, then if you heat it up by the same amount of temperature change, it will change longer. Does that make sense? Right? So the change will be larger, depends on the original length as well. So this is less, originally you might not think about it, but this is what happens. Okay, so that's part of the takeaway from this. Okay, so so what is it used for is this. So if you know the original length, usually you take a ruler, measure the original length, and then you know what change in temperature you're expecting. Then what you can do is you can predict the new length. You can predict that change in length, right? So if you know this side, you know this side, you can predict this side. Okay, if you know all these values from the lab, right, from table 17.1. And that is very important. Before I give you a few real life scenarios, let me plug in some numbers. You know what? Yeah, you probably see them in the discussion session. So I'll cover the other idea first, is when to use which one. So I'm putting this in a box because this is practical. It's a practical version that you will probably use most. Or there's one more, you can rearrange this and write out the left-hand side here is L1 minus L naught, right? So you can put the L naught to the other side as well. So you have L1 equals to L naught plus alpha L naught delta T, like this. This is another useful, because a lot of times you actually want L1 as I just shown in here, right? So you actually want to know L1, so this is good. Now, quick exam tip, which one should you use to start with? All three of them, whether it's the original definition or one of these practical versions, they're all fine. Okay, so this is one of the rare cases. Usually, in exams, usually we'll tell you to start from the most fundamental one and then derive your way through and then plug in the numbers. But this one, it's fine. You can just directly start with this. So when to use which? Just a quick comment. Is, as I mentioned in Word already, if the length doesn't change much, what that means is, so when an object has a base area times length, right? That's what the volume is. So if the length doesn't change much, that means the area changes, the change in area is dominant, right? That's the most important one, if the length doesn't change much. For example, if I have two hard brick walls and I squeeze a piece of cheese or whatever in between and I heat it up, the only way it can do is expand in this way, right? So let's say you have a circular disc so now the area of it is expanding. If I constrain that the length is not allowed to expand, then use, right, alpha A. If the area doesn't change much, i.e. the change of length is dominant, when is this situation useful? This situation is, for example, let's say you have a long rod. So now you have a length, and then you have a cross-sectional area, right? So technically it expands in all directions, but which one is more important? Because the expansion of length is proportional to the original length, and fractional area is proportional to the original area, right? Delta t, the delta t, let's say, is the same. Sorry, same, not cancel out, but same. Which one is more significant? If this is larger, then this is going to be more significant, right? If this is small, then this is going to be small because it's proportional, right? So as in this case, then use this because that is enough. And if none of the above, so if all three dimensions are similar, then use the volume one. And also a quick comment on the units. So the SI base units for temperature is Kelvin, okay? We'll talk about that more in tomorrow's lecture. Yes, tomorrow's lecture on why that is the base unit. For now, accept that fact first, not Celsius, not Fahrenheit, not centigrade. Conversion, in case you don't know, is a shift. Now, this is a very rare scenario in physics. Usually our units are proportional. So from miles to kilometers, whatever, it's proportional, but this is a shift and it's very different. And you have to take care of that. Let's say if you have X degrees Celsius, then you shift it by 273.15. For now, just remember 273. You can check the book if you need that 0.15. Yeah, right. The conversion will give you usually in exams. You technically don't have to memorize it, but it will be a benefit because you're going to use it so many times in the problems, right? So if it's so if it's 20 degrees Celsius, what does that mean? So you plug that in, right? 20 plus 273K. So that is 293 Kelvin, right? So room temperature is roughly around 300 Kelvin. You can do it the other way around. How about 300 Kelvin? How much Celsius is that? So you need to flip this around. And let's say this time you have Y Kelvin. And that would be, if you're confused how to do this math, by the way, just let this be Y, right? So Y Kelvin. So what is Y? Y is X plus 273. So X is on the left-hand side. So X must be Y minus 273. That's how you calculate it, right? But usually it's quite intuitive. You don't have to use a formula like this. So so this is 300, right? 300 Kelvin, the degree in Kelvin, and then you subtract 273. That will give you the Celsius. So so that would be 27, sorry, Celsius. A quick notice: you see, when we say Celsius, it's degrees Celsius. When we say Kelvin, it's Kelvin. It's not degree Kelvin. Okay. Sometimes people write degrees Kelvin. Always bugs me. it's like newtons, or kilograms, or it's not degree newtons. It's Kelvin. It's a base unit. That's it. We won't deduct you. I'm sure there's people who are going to write it to degree Kelvin. We won't deduct you points for that. But yeah, just for your information. Now. The danger is this in red. Sometimes people do this. They will say, if you have something like a fractional change in temperature, and then they plug in something, okay, let's say the change is 3 degrees Celsius, and then the original one is 2 degrees Celsius, and then they go, okay, I'll cancel this. So the fractional changes, or let's say the original, let's say originally it's 6 degrees Celsius, and then they cancel, and then they say, okay, so now it's 0.5, right? So now it's 0.5 or 50%. Wrong. The Celsius cannot cancel like this, okay? What is the correct way is this has to be in Kelvin. So let's see what the right way is, because it's a shift. So let's do the dumb way that we know would definitely be right. So you change it to Kelvin first. So so let's say the original is 6 degrees, the new is 3 degrees, right? So the 3 comes from 6 minus 3. So you first do 6 plus 273, that's the original amount of Kelvin, minus 3 plus 273 amount of Kelvin. So on the top, what do you get? So you see the 273 actually cancel out if you do the math at home carefully, if you're not following right now, if I do it quickly. So you get 6 minus 3, and then on top you still get 3. And you still get 3, but this time you get 3 Kelvin. If you factor out the Kelvin, right? You factorize the Kelvin out of the brackets, out of the parentheses. All right. So first of all, you see what's wrong already. The top, initially when you wrote 3 degrees Celsius, that's not right. It should be 3 Kelvin. And you certainly know the difference between 3 Kelvin and 3 Celsius. It's different. This is right? Because we use the rule of start with SI, you end up with SI. But here, all right, how about the bottom? The bottom is a bigger worry because now the bottom should be, the correct way is this, right? So it's 279 Kelvin. And then, yes, now the Kelvin cancels. Now you're allowed to, because it's SI base unit, that is the fundamental unit we use. And then you get a very small number, not 50%, right? I'm not going to plug it in the calculator, but actually that's around 3 over 300. So that's around 0.01, right? So roughly estimate. So be careful, all right, here. All right. Now, sometimes you can use, there's an exception. If you know what you're doing, you don't have to convert it to Kelvin every time if you know what you're doing, okay? So what is the exception? The exception is this. If you just need delta T, not delta T divided by some other temperature, but delta T on its own, okay? Why is that? Because delta T is, let's say, it's T2 minus T1, right? So let's say it's X Kelvin minus Y Kelvin, okay? So what is it in Celsius? So let's change that in Celsius. That's X minus 273, right? So Celsius is always the smaller number. Kelvin is a huge number. Even it's not very friendly to use that every day. That's why you don't use it outside of science. But if you do scientific calculation, you need to. And then it's Y minus 273 Celsius. Okay, so expand this out, right? Factor out the C's, the Celsius, degrees Celsius. Now you have X minus 273 minus Y plus 273, right? So this cancels. Now you have what? You have X minus Y degrees Celsius. And you see, whatever, that is the same. So the conclusion is 1 degree C change is equals to 1 Kelvin change, the change of 1 Kelvin. But this is so important, the word change, because, can't emphasize this enough, 1 degree Celsius is not 1 degree Kelvin, okay? You know that, right? So this is the warning over there. And my suggestion is very simple. When in doubt, use what? Kelvin. Change it to Kelvin and then come back. And then, yeah, change it to, if the question asks to give you a final answer in Celsius, and they give you the initial values in Celsius, yes, you have to do it the long way. Change it to Kelvin first, do your math, and then change it back to Celsius, unfortunately. After you do 10 problems, after your home 10 problems of this, not the 10 for the whole segment, right? Then you start to see a pattern, and then you know when to just do it the quick way and no need to go back and forth, right? So you develop that pattern recognition. Good, so this leads us to the last thing of real life applications. This is pretty fun, actually. So the first part is that there's not much math going on here. I'll just sort of talk through it and write down some notes. For example, the door creaking is one thing we probably notice from a very young age, that when you go into summer, your door starts to creak when you go in and out. It's because your door is expanding with respect to the frame. So let's say this, by the way, the frame is going to expand using which coefficient? Let's say your frame is made out of concrete. So it's the walls, basically, and then your door is made of wood. So are you using the alpha of concrete, but which type of alpha? Length, area, or volume? So look at the frame, right? It is mainly a length, so you use that. So you use that for the concrete. You look up the alpha L for concrete. Whereas for the door, you look up the area for wood. Okay. Right, so that's one thing. All right, so one example, so this is probably the major one, is it explains a lot of the damage just to structures. Okay. So I'm not going to write out too much, but let's show you some examples. You see, this is what we call bad engineering. What happens when you do not take into account that you forgot that this railway will expand. Look how scared this guy is standing right there in front of the railway. Which type of expansion do we use for railway? That's right, linear, right? Because it's long, right? So this is what happens if you don't care, if you forget. So that's why the railways always are built in segments like this, and then they have tiny gaps over here. And these gaps is to allow for some of the temperature variation between summer and winter, and you won't cause disasters like this. Another one you see is in road pavements, right? Is sometimes probably not so much in California, but in places in maybe Michigan or whatever, with very high variation of temperature between summer and winter, that they can go to extreme sub-freezing temperature, and then they go to very warm temperature. The roads would expand and contract a lot, and you'll see these gaps to try to take care of that. Otherwise, they'll bulge out, and cars would start tripping on them. Right? So this is good engineering. This is bad engineering. And you see, this is also explaining why sometimes when you never pour boiling water into glass, because glass is extremely brittle as well. And if it tries to expand more than it should, it's not even flexible to bend, and it will just break. And if you ever have tried cooking and putting glass inside an oven, don't. You know what happens. So that's the reason why. This is another very interesting idea of engineering. You can use, so when you have these long pipes, you want to deliver pipelines of oil or gas from one place to another, you have long length of this, and you can't really make a gap like this. So engineers are really clever. Let's give them that. If you bend it like this, now part of the bend would go up and down. So it will not sort of bend like this, but it will stretch. So part of it will stretch up and down, and part of it will stretch left and right. And so you won't have the whole lengthy, a whole mile of pipe just bulging on one side. So it redistributes some of the bulging to upwards motion. So that's a nice, clever one as well. All right. So how does the glass break where works? It's also discussed in the book, I think. Don't worry. Yeah, you can Google that more. Just for time purpose, I'll give a few more examples first. If you're interested, you can just Google that. And here's another very clever one. So I thought this is very clever, at least number 3, is used to fit parts. So fitting parts of things. So let's say you have a peg and you have a hole and something, let's say you're doing some woodwork and you need to fit a nut inside a hole like this. And you want it to fit very, very snugly. So you want it to be very tight so that it doesn't come out easily. It can be a screw, by the way. So what you can do is you first cool down the object, I'm exaggerating, and then put it in the hole, and then leave it to expand it back to room temperature. And then now it will fit extremely snugly, because originally, let's say it's a little bit larger than the size of the hole, right? Then it fits extremely snugly. It's extremely hard to pull it out unless you break the whole thing. And so for very important engineering, if you put a screw inside something, sometimes that's exactly what they do. You can either expand the material, depends on what easier. Usually you cool down this and then put it in and leave it expand, or you can expand the hole and then put it in and then leave the hole to cool down and fit tightly snug around it. Right? So that's one thing. Of course, number 4 is a thermometer we talked about. Now, for thermometer, it's a little bit subtle about which you should use. Should you use the volume, or should you use, so you have a liquid inside. Should you use a volume, or should you use the linear one? Now, this one is, first you might think it's linear because this is very long, right? But this part is the majority. This is the dominant. This is only a very small part of the whole liquid. This part is the dominant expansion. So what you calculate is actually calculating the volume one, right? And then this part is, yeah, the other part is very insignificant. Okay. Also, just as a reminder, the textbook, this is called beta. Okay. The textbook doesn't even mention area, but sometimes it's very easy to get confused. What about area like that? So I think that is it. All right, so that's pretty good. I still have a few things to say, but I think I'm starting to do better on time. All right, so good. So this is the end of chapter 5. Right, these examples conclude that. Then now I'm going to the next chapter. What I'm going to tell you is we're going to go through it very, very quickly because it is a nature of two things. Nature of 3B is really a very, very intensive course, to be honest. There's so many material to go through. There is some topics we'll go through in brief, and we won't examine too much. Is, for example, when we get to real gas and vapor pressure, those topics, some things in brackets, you see I say limited examinability. That means we won't examine too heavily on those. Another thing is one of the chapter, which is thermophysics, part of this will rely on your own self-study, and that is the next chapter. The next chapter is about specific heat capacity, and I'm willing to bet, at least historically when this class is taught, capacity and latent heat. Right, so sometimes called calorimetry problems. Sorry, calorimetry problems. I'm willing to bet that a lot of you have already some basic familiarity with this topic. You will heard of Q equals MC delta T. What I'm going to tell you is I would suggest you for physics, put a delta in front. Get used to that. It will make a lot of the things much more symmetric and as a result, easier. Because something changed on this side, something should change on this side, because later on you're equating to, for example, changing gravitational potential energy or something like that. Remember on yesterday's lecture, sorry, so just to let you know where I'm going with the last 8 minutes of this lecture is I'm going to give a very brief overview of things you need to know in this chapter. You can read it up and do exercise on that. I have full confidence in you guys, you'll be able to take care of that. And tomorrow's lecture in the beginning, again, I'll re-emphasize, and also hopefully you have done some reading on this already. So the reading is, and then I'll just add a few extra points on that. And yeah, the other would be reliant on self-study. So that's my comment on that. What is the reference chapter? 17.62, no, that's not it. 19.3.5, 3 to 5. 3 is specific heat, 4 is latent heat, 5 is applications of specific heat and latent heat. All right, yeah, so that is the plan, right? So this is a formula you need to know from this chapter. And let me make a comment is, remember yesterday we talked about Jules was the first guy who, by spinning paddles in water and putting a weight over here, letting the weight, let's say you put a 1 kilogram weight like this, and then it spins, and then he realized he used a thermometer, which we talked about how that works, and then measured that the temperature increases. So he realized a change in gravitational potential energy causes a change in temperature. See, right? So it looks much more symmetric that this, remember heat is a energy transfer. So this is a change. So it's transferring certain types of energy from here to temperature to here, like that. So everything is a change. It's better than, sometimes people would just plug in a number like this without remembering that you need to do initial minus final minus initial, like that. Okay, so that's my recommendation there. A lot of textbooks don't do that. And I'll explain a little bit more why they don't do that tomorrow. So that the next one is latent heat. So the latent heat is you will probably have seen this formula. Don't copy this yet. I'm going to make a minor adjustment. Okay. You probably have seen this formula, and there's a latent heat of vaporization or latent heat of fusion. Okay. And as I say, I would recommend, this is a very powerful tip I developed myself, that it makes things so much easier to visualize and understand, as well as doing practical problems, to put a delta. Now, originally, it kind of breaks down my justification, right? I said, this is great because look at the symmetry. Now everything makes sense. But now it seems to break that out. Where's the delta? There is a delta. And by putting in the delta, now you can copy it, by putting in the delta, is what will take care of a lot of people's mistakes in their solutions. The delta goes in, believe it or not, in front of the M. Okay, so if you like, you can put a bracket around it. Let me explain what that means. latent heat of vaporization. So forgive me if I'm going to speak as if you know some sort of basics. If there's some percentage of you who have not encountered any of these three formulas before, and I'll rely on your self-reading, and on discussion session you'll get some examples as well. You can go there. All right. So what is delta M? What is latent heat of vaporization? So this is a constant that tells you how much. I'm going to give you the layman definition. How much heat needed to vaporize something. So it means vaporize means taking liquid to gas, or vice versa. This is all reversible. All physical reactions are usually reversible, because there's exceptions. And this is the constant that tells you how much heat needed to, I guess, fuse something, but to melt or what's the condense, the opposite of melt, something. Okay, so that's changing it from between solid and liquid. So this mass you put here is actually the mass that is melted, not the mass of the object, okay? Some people would give you an example, and this is the mass that is, melted belongs to the bottom, and mass boiled. Sorry, this is not condensed. This is boil or condense, depending on which way you go. And this is melt, or what's the opposite of melt? Freeze. Right, so subscripts, probably by now you have an idea that I am a fan of subscripts because it tells me what I'm doing. Let me show you what can go wrong. Here. So if I have an ice of 1 kilogram, and then let me put it in water, and then after a while it melts a bit, and then now I have a smaller piece of ice that is 0.3 kilogram. So if I want to calculate how much heat is transferred from, okay, first of all, from where to where? So which one is gaining heat, which one's losing heat? Which one, so the ice is melting, to melt it must gain heat, right? So the heat is going in this direction, from the water to the ice. Remember, heat is always from something to something, right? Remember I wrote from last lecture, remember I wrote 1, 2, right? From 1 to 2, object 1 to object 2 or something like that, okay? So what, from water to ice, how much heat, right? So you plug in, let me tell you that L fusion for water is 334 kilojoules per Kelvin. You can look that up in the table. All right, so you're going to plug in this. Okay, so 334 kilojoules. So the kilo has to be put in here, right? So 334 K. So K means times 10 to the power of 3. So what do you plug in for the mass? So I've seen the mistakes that people plug in 1 kilogram. Of course, that's wrong. People plug in 0.3 kilogram. That's wrong. You plug in how much that is melted, right? So that's why this label over here is useful. Okay, so how much is melted? It's 0.7 kilograms. Okay, it's 1 minus 0.3. All right, so sometimes, of course, the problem will tell you exactly how much melted. Sometimes the problem is going to be a pain and trying to just tell you what is left, and then you have to figure out what is actually melted. Right, so that is that. Right. All right, perfect, good. So I will fill in some. I've done pretty good job today on time. I'll see if I can keep this up. I'll make a few more comments. So if you have to leave, say for that, but it's not going to be more than 3 minutes or 2 minutes. So I'm breaking up the chapter over here so that you know what to read for tonight. Probably after the test, you might want to focus on that first. I know you're worried about that. And after that, so do a little bit of reading. In fact, if I were you, my suggestion is focus on reading this first before you review this chapter, because I want you to do a little reading here, and then tomorrow in the beginning, I will give you supplementary insights, that things that the textbook might not have said, things that from experience I think are common mistakes. If it's not too much, maybe I will actually just do an example for you in real life, in real time maybe that is actually a good idea. Now that I think about it, I'll just do a actual example, example or two, so you see what is expected of you in physics to how to use these formulas, and I'll show you also how the delta Q is in play. Okay, all right. That's all I say. If there's no other questions, thank you very much, and good luck.